Okay. Without much ado.
Hi, everyone. Welcome to the CIS seminar series for the fall of 2024. I will be with you throughout this semester, actually this academic year, for the welcoming our amazing speakers. And today, please join me. Welcome Dr. Grover Swartzerlander. Dr. Grover's research interests have spanned a range of topics in optics, including advanced imaging concepts, force-based application, radiation pressure, optical vortices, nonlinear optics, coherence, geometric phase, and metamaterial. He's a fellow of Optical Society of America, and NSF Innovative Advanced Concept Fellow, and NASA Innovative Advanced Concept Fellow, and NSF Young Investigator. Dr. Grover served as a topical editor for optics letters, and he was editor-in-chief for Journal of Optical Society of America from 2013 to 2018. Dr. Grover received his PhD from Johns Hopkins University and MSc from Purdue University and BS in physics from Drexel University. Please join me. Welcome, Dr. Grover.
Thanks, Dima. Thanks, everybody, for coming here. I'm showing here some footage from the Planetary Society they put out for their LightSail 2 mission that orbited the Earth successfully for 3 years. Just to give you a little bit of highlight about some of the cool stuff that's involved in launching solar sails, deploying them, and what I'll be talking about today is doing some science with them, actually a science payload. And let's see. So this work is supported by NASA, actually what's called the NASA Innovative Advanced Concepts Program. We've been awarded a phase 1 for this project, a phase 2 for this project, and a coveted phase 3. The phase 3 is awarded to only one group every year. Some years they don't even award it. So it's very prestigious. And it basically, the rationale for the different phases is to increase what's called the technical readiness level, or TRL. So we're expected in this phase to basically have the technology kind of ready to be handed off to the aerospace community for actually doing a real mission. So we're actually in the process now of trying to propose this through internal funds at the Applied Physics Lab to develop a heliocentric, solar polar orbiting imaging system. There are some of the best heliophysicists at APL who are very interested in seeing this mission proceed forward. We've had, so basically Johns Hopkins Applied Physics Lab is the serving as a current PI. Actually, my former BS/MS student from mechanical engineer is now my boss, and she's the PI for this $2 million award. We do work with Beam. It's a company in Orlando, Florida, that makes advanced polarization optics. We also work with a local company, Viavi Solutions. They make basically engineered diffusers, and they're looking at making some sample materials for us for solar cells. This is an artist's concept of what our diffractive cell might look like. This was actually designed by a graphic artist here at RIT. All right, so I do a lot of different work. Let me see if I can get rid of this. How do I get rid of this? Oh,
you got to go all the way over here. You got to use the mouse on the other screen.
okay.
Oy, 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 oy.
I'll be X there. Okay, thanks. Another X. All right, thank you. Okay. All right, so my research interests currently are quite broad, and I've had experience doing a lot of different stuff in my career. Obviously, the Young Investigator Award was awarded many years ago. Solar sailing is high amongst what I'm doing now, but we're also doing light with basically protecting sensors from laser damage. You can imagine if you're at a rock concert and you're at the light show is sending a pretty green argon ion laser beam around, and your cell phone happens to catch that, it could fry your camera. And so we're interested basically in systems like that, and systems that are probably much more expensive to protect them from laser damage. So we're using deep learning and engineers diffusers for that. are doing work with what's called the vortex coronagraph, or making very high contrast imaging. I initially proposed this for looking at exoplanets, and that was successfully done. Now we're looking at actually using it for looking at femtosecond laser filaments in air as an example. And then I have another program that is basically funded through an STTR, through DARPA, and through this company Beam, for looking at crystal optical elements for making very lightweight, very advanced optical materials for a variety of purposes. All right, so let's see, I can't get this. Come on, where's my cursor? Let me get to the next page here. Oh my God, do I have to go down there? Let's see if I can't. There it is, okay. Advanced, there you go, okay. So with all this kind of work that I've done, I've developed, and me being here for a while, I've kind of developed an idea of what we could do to kind of bring a new element to RIT, specifically to the Center for Imaging Science, and that's my long-term proposition. I'd like to propose to folks who are in remote sensing area and other areas here in imaging science and some across campus, is to establish a helio remote sensing expertise in imaging science. And that's going to build on the terrestrial remote sensing legacy we have here at RIT, but it also integrates the newly established deep learning capacity we have with some of our new faculty, okay? And it's also going to introduce a strong polarization optics component to the curriculum, because these, as I mentioned earlier, this work we're doing with Beam is basically another way of controlling the phase of light in order to produce things like lenses, mirrors, diffraction gratings, all kinds of exotic optics that are very lightweight. And it's really, they're such a busy company. They're hiring my students, and they are basically changing the size, weight, cost of many optical systems. This proposition also would bring in partnerships with other College of Science enablers, such as an AST in math, chemistry, and material systems, and certainly bring opportunities for students in employment and internships. And perhaps even with a grand vision, if I may, introduce new faculty lines to support this kind of helio remote sensing in aerospace. Could be people with real hardware experience, launching CubeSats, for example, people with understanding of heliophysics and the imaging systems for that, specific sensors, lightweight sensors for doing that, using AI, energy storage, all the kind of enabling technologies that you need in space. If you're studying the space economy, you know that there's actually even ETFs traded on the New York Stock Exchange that are basically just dedicated to space. Space is basically, let's say about a $500 billion industry right now. 80% of that is basically driven by the commercial sector. Most of that is like SpaceX and places like that are for launch systems and for communication systems. Communication is key to our modern technology. 4G, Internet of Things, all this stuff is basically, if we lose our satellites, we lose a whole lot of capacity, and the modern economy is going to suffer because of that. So it's very important to understand the sun, because that sets the conditions for our space environment. And if we have like a solar mass ejection that hits the Earth, we lose a whole lot of capacity. And I'll be talking about that a little bit more. So there's the various funding sources and folks that are interested in supporting this type of idea. So early on, I want to acknowledge, because I'm sure I'm going to run out of time. I think I only have an hour and a half. Is that right, to talk? Is that right? Yeah, something like that. Okay. So just kind of joking. Not really, but I'll go as fast as I can and try not to lose any of you. Okay. So I got a couple of students working on this presently. Ryan Crumbs, Ryan here. Shirley and Sean here. Is Keshav here? Keshev's probably busy working or is in the class. Keshav is a computer science master's student by some of my past students, including Ching Wang. She's now at Viavi Systems and here in Rochester. Amber Dubil, who's now at the Applied Physics Lab. She's my boss. Lucy Chu went to Facebook. Pratik went to Apple. Aaron went to Beam. He was BSMS student in mechanical engineering, and the list goes on. So we've got, you know, a lot of students who have participated in this over the years. My current collaborators are Applied Physics Lab. Besides Amber, there's Angelos. He's probably one of the top heliophysicists in the country, if not the world. I've got a number of people working on making devices there with their fab facility at APL. And I've got a number of people who are working on basically GNC, guidance, navigation, and control, and orbital trajectories at APL. In addition, I got the team at Marshall Space Flight Center in Huntsville, Alabama. Les Johnson, he is the basically leading expert in NASA on solar sails. He's developed a number of missions, been the PI. His team are also doing work with GNC with space weather testing. They got a facility there for bombarding our samples with electron beams, with UV light, and doing thermal vacuum testing. Beam, our collaborators down there, are making some samples for us. Viavi's making some samples. In the past, I was working with the University of Utah and Alabama, making samples and doing some modeling. And special thanks go to my colleagues at RIT, Steve Weinstein, who's helped us out with some theoretical work, Rich Halstone, who's coated some of our samples with gold, Zoran, who's helped us with the students make some space weather testing at Goddard, Michael Richmond, who's in physics. He's basically helped us get a facility in the basement on John Street in the astronomy facility there to set up our torsion oscillator. By the way, we have probably one of the world's best torsion oscillators for measuring radiation pressure. No one's been able to match what we've been able to do. Michael Mihai Barbosa, who basically sends us students from SpaceX, SPEX. SPEX is a space exploration group at RT. If you're interested in space at all, you should look into joining SPEX. They meet weekly. They try to design missions that help the students. So since we don't really have an aerospace major, these students are basically, and some faculty are basically involved to try to give them experiences. Our librarians, people at the SMFL who help give us space, and the list goes on. So this is a picture of Les Johnson, who's at Marshall Space Flight Center, Amber DuBill, and this is me here. We're basically at in Huntsville, where they're actually testing the solar cell that was being ready to deploy. This was the NeoScout mission. This mission went up, gosh, I guess about a year ago. Well, it went up, but they never heard from it. So this was unfortunately, they set up a lot of secondary payloads on this first launch of the SLS, and most of them basically failed. This shows how difficult space can be. They don't know whether these payloads actually deployed out of the holding or what happened, but sat on the launch pad for a long time because of delays. And so this is just part of the learning curve for space. Now, I want to read the abstract to you because there's a number of things I want to point out to you. So it says, with the emerging space economy, remember the space economy. Okay, this is like a $500 billion a year and growing aspect of the world we're living in now. Okay, comes with great concern with planetary defense. Okay? Planetary defense. This is a term you'll hear bandied a lot about. It basically means not just asteroids, but also things like space weather, coronal mass ejections, and such not. Okay, from rogue coronal mass ejections, sun-grazing hazards. You might remember the Chelyabinsk meteor that struck Russia 2013, I believe. Came out of nowhere, apparently. Okay, they didn't see it coming because it basically grazed the sun. It was basically in a blind spot. Okay, so basically, this says that we need to do a lot more for planetary defense. Besides the need for better understanding of space weather, space agencies like NASA, NOAA, they launch space satellites to unravel the mysteries of the sun. Right? The sun is our closest star. How many people we have here in AST studying stars? Okay. How many of them are actually studying the sun? Very few. There's so many mysteries about the sun. There's so much opportunity to understand the sun so much better. And this is like an opportunity I think, for universities. Okay. So unravel solar mysteries, such as reasons for the surprisingly hot corona. We don't know why the sun is so hot. The interior is cooler than the perimeter of the sun. Okay. Why? How we can predict solar flares what's driving magnetic reconnections and the enormously large solar wind acceleration. The solar winds are coming off and being accelerated, and we don't even know really what the forces are that's driving that. There's lots of things that need to be resolved. It's our neighborhood. To help resolve these concerns, my team, which includes mission specialists from NASA and the APL, have proposed launching a constellation of solar polar satellites to provide scientists with data, allowing the construction of better theoretical models and deep learning solar prediction networks. Okay, we can look at our cell phones and predict look at the predictions for the weather a week out right now, right? But with solar weather, right, we're lucky if we can get a day in advance to kind of get some feel for how much you know, of the sun's you know, radiation, how much of the ion flows, how much of the UV and stuff is going to be hitting the Earth. Okay, we need to have better predictions for that because our economy is more and more based on that. So key to this mission is ability to achieve high inclination orbits. High inclination means above the ecliptic. Okay, the planets and everything, right? All of our satellites, all of our space missions are basically constrained to the ecliptic. Okay, to get out of the ecliptic is very difficult. It takes a lot of energy. Rockets alone cannot just get us there. So this is where solar sails come into play. Okay, so this talk will describe some of the potential of using diffracted sunlight to achieve these out of ecliptic orbits. Okay, so what do you see when you look at this picture? You see the sun. Okay, you know, if you're a historian, you might see basically the source of basically the first major monotheistic religion. Okay, this was Akhenaten, who basically considered the sun not a deity, but a god itself. Okay. What's that? Yeah. So if you're a historian, okay, this has a monumental place in cultures. Okay. It was basically, you know, drove many cultures. If you're a biologist, what do you see? You basically see the source of life, right? Chlorophyll, right? Okay. Chlorophyll needs this guy here. And without chlorophyll, we probably wouldn't be more than some kind of thermal vents, living protozoa or something like that, right? But, you know, yeah, you're right. If you're a scientist, you see a lot more, okay? You see a lot of heliophysics. You see all this magnetically driven plasma and magnetosphere around the Earth that's protecting us from these emissions that are coming from the sun, okay? There's lots of science that's yet to be described by these flares, by these connections, by the accelerations that I said. There's a whole list of things that are really fascinating from a scientific point of view. What I see here is what we don't see, okay? That is the poles of the sun. We don't know what's happening at the poles of the sun because no one's ever taken a space mission to actually go over the poles to image them, okay? There's been one mission, Ulysses, that went over the poles and it got some magnetic data, but it didn't carry any imaging. So that's what we'd like to do. We'd like to get out of the ecliptic, okay, and basically image the sun. Now, right now we have satellites at L1. Does anybody know what L1 is? It's like the first Lagrange point, right? It's basically a gravitational well that's basically established between the sun and the Earth. And we can put satellites there to get some advanced warning about space where they're coming. So by the time we call this distance 1 AU, right? This distance here is basically between the Earth and this L1 point is about 1% of the distance from the Earth to the sun. Okay, so we don't get much advanced warning. This is like a very, very short distance here. That gives us about 15 minutes to an hour of advanced warning time. Okay, yes?
Is it L1 inside the magnetosphere or outside?
Oh, yeah, this is, yeah, probably, yeah. It's probably outside here. This is an exaggerated picture. I'm trying to show a couple of things at once. Yeah. It's probably, yeah, it should be out here, I believe. But basically, on this scale here, yeah, it's very close to the Earth. That's the point I want to make here. And it basically gives us a perspective of basically just looking along the ecliptic at the sun. It doesn't allow us any perspective of the poles. Okay, so we can't imagine you were looking at a Michelangelo sculpture, okay, and all you saw was his nose. Okay, what would you be missing? Yeah, you'd be missing the entire sculpture, right? You couldn't say it's a great sculpture because it's basically all you can say it's a great nose, right? Okay, we need to know a lot more. Okay, the sculpture might be like the Pieta in the Vatican. Okay, has anybody ever seen it? beautiful, okay? You know, Mary's holding Jesus, it's very touching, right? But all you saw was Jesus' nose, you wouldn't get much out of that, right? It wouldn't have the same emotional impact. And the same thing about seeing the pole of the sun. We know that all orbiting bodies have very special dynamics. There's like Rossby waves, there's all kinds of things. There can be like on Saturn, I think they've seen the hexagons, right? There's all kinds of interesting phenomena happening at the poles. We don't have any access to that yet. So this mission will bring a great new perspective of the sun. Now, there are a number of satellites that are at L1 that are doing a good job providing us some early warning data. What we propose then is the solar polar mission to actually go over these poles. We actually propose a constellation of at least two. Two will provide us a stereo imaging pairs. Okay. Why do we have two eyes? Because we can get a lot more information than we can with one eye, right? We can get some kind of perspective. In fact, with anybody doing, remote sensing and stuff probably knows you can get volumetric data. If you have two images, you can determine a lot about the volume, let's say, of material inside of these coronal mass ejections, for example. Now we're going to place this at half a distance. Now this is going to give us half a distance between the sun and the earth. This increases the time from 15 minutes to 12 hours of advance warning. Okay. 15 minutes is almost nothing. What could you do in 15 minutes if you knew, let's say, a hurricane or an earthquake was going to come in 15 minutes, right? Can you imagine the total economy turning around, turning off, trying to protect all of the electronic structure in 15 minutes, right? Very difficult. 12 hours, okay, that probably is enough time to help protect a lot of assets on Earth. Okay. So we propose to put it here and to basically have a spiral trajectory to basically work our way to get high inclination orbits around the sun. All right, so this shows an example of image from stereo. Stereo is basically currently orbiting around the Earth. One is on the leading edge of side of the Earth, one's on the trailing side of the Earth. And it provides a little bit of parallax. It gives us some idea of what's happening at the sun. It's an image from that. And you can imagine, I call this a bad flare day, okay? You can imagine if this thing was heading toward the Earth, okay? How much magnetic field it carries, how much charge, and how many ions are being spewed at the Earth, causing satellites to fry, transformers to fry. In fact, I think I have a picture of what this looks like. Imagine, okay, if something like that hit the Earth. This is your computer, okay, after a big magnetic flux that goes through the Earth because of one of these coronal mass ejections. Power lines can fry, basically. Transformers will blow up, okay? I don't know if anybody uses these things here, okay? But if you do, you're in trouble, okay? All this stuff is going to be garbage, okay? Now, is this Chicken Little just saying, oh, the sky is going to fall? Well, we've seen in 1859, the Carrington effect. It basically fried the telegraph system that the US had just built. Okay? In Quebec in '89, it basically caused an outage. A solar flare caused an outage, coronal mass ejection. Sent magnetic field through their transformer stuff, knocked them out for a week. Most recently, SpaceX had a disaster. There was a flare that came through. What happens during these flares? Not only you got a bunch of charged particles, magnetic fields, but basically the whole atmosphere swells up. Okay, so these satellites are put in low Earth orbit. Okay, there's atmosphere there, and there's a little bit of drag from that atmosphere. But now, what happens if you fluff up the atmosphere? Now you're going to expose these satellites to tremendous amounts of drag. And what happens is they lost a whole bunch of satellites, and they had just launched. Okay, $100 million into basically just fell into the Earth. Okay, they didn't have enough power on the satellites to get them out of that dragging, that catastrophic drag trajectory. You probably might have looked in May up at the sky and saw a aurora here. It was gorgeous, glorious.
Yep. See, I sure can. Let me go wash my hands.
Could have caused damage. It caused some radio blackouts. So not all
Get him on.
G5 storms are the same as others. But basically, you can get a firsthand glimpse of what the sun can do. Just go out almost any night, and you can see the aurora. If there is, I'll show you a site where you can track to see when a good night is. Okay. But basically, we're at a solar maximum right now. Okay, so this is really a good time to kind of experience this. Okay. Now, what happened? 780,000 years ago, there was a magnetic field that flipped, and we're expecting the magnetic field of the Earth to flip again, anytime, okay, we're overdue for what's going to happen to our whole space economy with the shielding that the magnetosphere provides and stuff when these poles flip. We have no idea, okay, we've got to prepare, okay. At that time, the Homo erectus was the major humanoid form. They lost all the cell service. Okay, now there's no record and no archaeological record that they actually had cell phones, but if they did, they would have been, their teenagers would have been a bit upset, I think. Okay. All right, yeah, this just shows a few snippets from poor Elon. Okay, lost $100 million. Okay, back in 1922. Okay, from basically these satellites, they basically could not maintain their orbit because of the drag created by these corona hitting coming into the Earth. Okay, now the NOAA national has a National Space Weather Prediction Center, which I recommend you folks bookmark this. There's actually they're in charge of kind of tracking some of the space weather from these satellites. Okay, and that exist. And this one in particular is very good. You can look at this, and it gives you what you could expect for the aurora above Rochester within about 24-hour period. Okay, so it's a very nice sight. If there's clear skies, you want to see the aurora, then this would be great. I'd get out of the city a little bit. You don't have to drive more than probably half hour to get pretty good dark skies to be able to enjoy those. Now, so this. We want to make a case for solar polar imagers, okay, and stereo imagers. I mean, one is because there's a paucity of heliophysics data. Okay, we need more data to understand the sun if we want to be able to predict what's going to happen more than a couple of days in advance. Okay, the stereo provides this volumetric assessment, so we need imaging scientists to do this. We need somebody with deep learning skills. We need somebody that can basically pull all the data we get from our proposed mission and to basically put it into some kind of format that's going to be useful, so we can make real-time decisions about what to do, in the event that these things come crashing into the Earth. Okay, solar cells provide distinct advantages for doing these kind of missions because they provide unlimited amount of energy. Okay, it's not like a rocket. You have so much fuel and then it's burned and it's gone. Right, the sun's always going to be on. Okay, so you always are having continuous acceleration of these continuous propulsion. Okay, continuous acceleration, so you can achieve the orbits that you want. Now, the Ulysses mission, which was launched in 1990, they did achieve an 80-degree inclination, almost right over the poles. Okay, but it was a very large perihelion and aphelion, so it was not close to the Earth, not close to the sun. It was between basically the closest it got to the sun was between Earth and Mars. Okay, so and it went out as far as Jupiter. Okay, so it was not at the kind of close insight where you can measure things about what's happening kind of like between the Earth and the sun environment, which is what we want. Okay, but it provided a novel gravitational assist that allowed it to slingshot out of the ecliptic up over the poles. So slingshotting is one potential way of doing that. But it basically, when you slingshot, you're basically stuck. Your aphelion is going to be kind of stuck at that orbital radius, and so you're not going to be able to get a nice circular orbit around the sun that we want. It was also spin stabilized. Spin stabilized basically means that if you have something spinning, right? Basically, it tends to stabilize around the spin axis, right? Conservation of angular momentum. Right? So if you have a camera that's spinning, is that going to produce a good image? No. So we don't want a spin stabilized spacecraft. So this is one reason why they didn't put a camera on there. Okay. Proba 2 is a satellite that's basically in a sun-synchronous orbit. It means that basically it's always kind of looking at the sun, and so it orbits the Earth in kind of a lower orbit. And what people have done is they said, well, let's take those images of the sun that they've gotten from the sun-synchronous orbit and stitch them all together to try to get some kind of image of what the sun's poles look like. And this is what they came up with. Do you see anything here? Does that look like the sun to you? Right? It's a projection from a steep inclination angle that you really can't get a very good image of the poles. So these are kind of useless. Okay, we really need to get over the poles with a camera to get the information we want. Okay, now the ESA and NASA now have launched in 2020 a solar orbiter, and it's going to achieve an inclination of about 24 degrees in about 7 years. It's also using a gravitational slingshot. That's going to be basically kind of complicated. It's going to do Venus and Earth slingshots, so it's going to take some time to get there. And it's still not going to be able to achieve a very high inclination, but this will be helpful nonetheless. Okay, so we think our mission is going to be unique. We're going to get over the poles. Now you might just, why can't we just use a rocket to get there? Okay, well, we need a rocket to get up into space, but at that point we want to unfurl our solar sail and let the solar sail do the rest. And the reason we can is because this thing here called the rocket equation. Okay, it says the change in velocity of your spacecraft is equal to the exhaust velocity coming out the nozzle, okay, times the logarithm of the initial mass divided by the final mass of your rocket. Okay, so what this basically says is that delta V, what is delta V? V velocity, the change in velocity. Look at change in velocity is change in kinetic energy. Okay, 1/2 mv squared, right? So you need, when you're working in the in an orbit, you're basically working against gravity. You're in a potential well, and you need some kinetic energy to raise out of that potential well to change, where the location where you want to go. So you need so much change. And so when scientists think about space missions, they say, well, how much delta V do we need? So for example, if you want to go from the surface of Earth to an Earth orbit at 400 kilometers, you need a delta V of like 8 kilometers per second. Okay. If you want to get to a solar polar orbiter, you might need something in the 30s. Okay, so you're not going to be able to achieve that with a rocket, because in the best case, your exhaust velocity might be like about 3 kilometers per second. Okay, your initial mass, okay, about 85% of the initial mass is going to be the fuel. Okay, the rest is going to be basically the structure. So like they basically sets this ratio here. And keep in mind that the payload itself, the science, your cameras and all that kind of stuff, are going to be about 1% of the mass. Okay, so you're putting a whole lot of mass on the system. Most of it is just going to be basically exhausted out, or just structural mass. Well, nevertheless, you're not going to be able to achieve the kind of delta V's you want to get a solar polar mission. Now, anybody know who this fellow is? Carl Sagan. Very good. Anybody know who this guy is? Johnny Carson. Yeah, Johnny Carson was the guy before Jay Leno, I guess, right? The Jay Leno panel, Johnny Carson? I think so. Now who is it? Who is it? Jimmy Kimmel? No. Val, I think, yeah, one of those two, yeah. So anyhow, Carl Sagan proposed, and this shows from 1976, he proposed putting a solar sail up to chase Halley's Comet. They wanted to look at the comet and to do a flyby of the comet. Well, unfortunately, NASA said that the technical readiness level for solar sailing wasn't advanced enough to do this. So they said, okay, we're going to go off and start our own group. They call it the Planetary Society. The Planetary Society was the first crowdsourced funding organization that raised a lot of money to try to put up a solar sail, and they successfully did it recently. Now, one thing about Carl Sagan that I think is probably one of the most profound things that you're ever going to read was this little essay. I think he calls it a pale blue dot. Okay, now I want all of you to read this. Okay, just Google pale blue dot. It's just like a couple paragraphs. Okay, it's not very big. And it's so moving. I almost, come to tears whenever I start reading it. I try to read like once a year because it's just so profound. Okay, what's the pale blue dot mean? It's basically, he begged NASA to take one of the Voyager missions and turn the camera around, take an image of the Earth when it was like passing, even past Saturn, I believe. And when he did that, the camera caught 1 pixel. You're all imaging scientists, right? Is there much in 1 pixel? Would 1 pixel make you cry? This pixel will after you read this. Okay, it's just amazingly moving. Okay, puts so much into perspective. Okay, so I'm asking students to write an essay. If you're interested, I'll give you $20 for the best essay. Okay, write an essay about how it moves you. Okay, read this and just tell me if it's not as profound as I'm claiming it is. All right. Well, there's a long history of radiation pressure. It goes back to Kepler, talked about comet tails and these kind of things, went on to Maxwell, went on to early 1900s. Tsiolkovsky. Tsiolkovsky was the guy who wrote the rocket equation. He was thinking about solar sailing even back then. NASA actually used it to save a couple of space missions. Okay, they used radiation pressure to offset some of the angular momentum that had built up on their systems so they wouldn't be lost. Okay, then in the early 70s, Sagan, Friedman, and others, they basically formed the Planetary Society and started really trying to create a lot of noise. But this is like the early days of the Wright brothers right now. You know the Wright brothers? Okay, they basically pioneered, travel through the air, right? Flying, right? Okay, we're at that stage right now. Okay, it's taken us this long, over 100 years, to try to develop enough technology, enough enthusiasm to demonstrate solar sailing in space. This is what the Planetary Society put up. This was their sail. It basically sailed for like 3 years. And basically just used reflection, the law of reflection. The light comes in, bounces off this sail membrane, and basically produces a force normal to the sail. Now this does work. It's just not very efficient for many kinds of space missions because you have to tilt the sail at some angle. So it means you're not facing the sun. Okay, you're basically at an angle. So now the projection angle of light onto the sail is reduced. So our proposal is to try to find ways that we can use a sail facing the sun, get the full brunt of the sunlight to get higher efficiencies. Okay, so a main idea about radiation pressure is this. You got light coming in and light is scattered at some angle. Okay, so there's the incident K vector. K is like 2 pi over the wavelength. Okay, it's a magnitude. It's a vector. It basically, you're multiplied by h bar, Planck's constant. It's in units of momentum. So we talk about this as being the momentum in, the scattered momentum out, and whenever there's a change in momentum, what does Newton say? There's a force, okay? And so there's going to be a force that's basically proportional to this change in momentum. If we normalize it, we divide this change in momentum by the magnitude momentum and multiply it by this projection factor and cosine of theta, this tilt angle, we get an efficiency. And this efficiency is going to depend on the wavelength of light as well. Okay, so that's really all there is to radiation pressure. Okay, there's 2 components of radiation pressure, if you like, is a vector. Okay, so the force, if you like, there's a force. But this is the sunlight coming in here. There's a force along the sun line, and then there's a force perpendicular to the sun line. We want this perpendicular force to do our orbit transfers. Okay, so we want to spiral in toward the sun, and we want to spiral up around the sun. We're most concerned about optimizing this. This is small, it's negligible, it doesn't really have much effect because it's basically dominated. This force is working against the radial force, gravitational force of the sun. It really doesn't do much for our orbit, but this one is basically giving us all the ability to change our orbits, to spiral in and go up. Okay. All right, now we can measure this force in our laboratory. So this is our torsion oscillator. This is a vacuum chamber. We have a little torsion rod, basically a filament. This filament is, 25 microns? Is that right, Ryan? Okay, about 1/4 the size of human hair, okay? And it's supporting this copper rod, okay? And we put a little sample on one side, we shine a laser beam on it, okay? And when we shine a laser beam this way, then what happens, this thing starts to rotate, okay? Deperturb, okay? We can measure the deflection of this torsion rod. And by doing that, we can measure very precisely basically fractions of a nanonewton of force, okay, which is what we need. We have a laser about like a 1 watt laser, okay. So with a 1 watt laser, we can get enough force to move this torsion oscillator and demonstrate certain cool things about radiation pressure. All right, so we're working on advancing this system now. We're replacing this bell jar here with a vacuum system so we can do some weather experiments. Now, one of the experiments we did this for what was called Breakthrough Starshot. Breakthrough Starshot was a very ambitious foundation-supported project. They wanted to use a small laser of about, I believe it was about 10 gigawatts. Anybody know what a gigawatt is? A power station for a large city, okay? The electrical generator might be about 5 gigawatts, okay? So this thing is going to be a huge project, okay? But they just asked principal, could you use a laser, shine it on a solar cell or a cell of some kind, and basically catapult it to basically Proxima Centauri, Alpha Centauri, to the exoplanet, and get a picture taken there, and then send it back. Okay, that was what we were funded to do here. And the question is, how do you keep the laser on the sail, or how do you keep the sail in the laser beam? So we developed this system. It's basically two different types of diffractive materials. One diffracted the light downward when it was hit the top, hit the bottom, diffracted the light upward. So this thing was always being pulled back into the laser beam. And we got some papers published on that. But it basically showed that we were able to measure this in the laboratory. Okay, what we were able to do is we were able to show by turning the laser on and off, for example, we were able to take this oscillator that was going wildly like this, and basically we almost stopped it, okay, just with laser light, okay. This is called parametric cooling. It's similar to if you're on a swing set, okay, you're accelerating yourself on the swing or decelerating yourself to try to slow down. It's a similar kind of process, but we're doing this with light. Okay. How are we doing on time? I can go on for days. Okay. Another hour? Oh, okay, okay. So this is what a sail looks like in space. Basically, there's the gravitational force of the sun. There's radiation pressure forces, let's say X, Y, and Z, different forces. We can control those by just orienting the sail in different directions. And we can solve the equations of motion. You got a radial force, you got basically an azimuthal force and a polar force. You can solve all these. And frankly, this is why I think rocket science is hard, okay? They talk about rocket science, it's not rocket science. This is actually more complicated than it even looks, okay? Basically, what you need to do to achieve your orbit, you start out at some point in space with at some position, some velocity, and you need to end up at some other point in space at some position and velocity. It's just Newton's laws, but how do you achieve that in the most optimal form, constrained by what your system can do, is no easy task. And it takes a lot of smart people to figure out how to get these orbits done. What we figured out we could do with this system is with our diffractive solar cells, we can just take it and as it's orbiting the sun, we basically have it always facing the sun, hence the sun, okay? And as we rotate this thing, okay, as it goes around the sun, we just rotate it gently like this. We can basically spiral in toward the sun and get a high inclination angle. So it basically comes in, spirals like this, and goes up along that. Okay? That's our approach to doing this. Okay. Now, how do you make these cells? How do you make these diffractive cells? There's several different techniques. You can use traditional blaze gratings, which is just basically like a bunch of little microprisms. You can use these polarization optics, which are a bunch of molecules that are basically just rotated as a function of space across the sample. This shows a micrograph of what one looks like here. And or you can make what's called a metamaterial. And what's really important here is what the period is. Okay, the period of this repeat period. Anybody here taken Fourier or had Fourier? You know Fourier series? You know Fourier series. You can figure out how light diffracts from these things here. Okay, at least the first order. Okay. Well, I don't have a lot of time, but I do want to give you one important tidbit here about this panchiranthem phase, or this geometric phase. It's really quite simple. You could be hearing a lot about it. Basically, you take light's electric field, right? Okay. Circular polarized light basically has an XY component. One is out of phase by 90 degrees with respect to the other. So we can represent this as just some real part plus odd times the Y component. Okay? And if we want to change a two-dimensional vector, okay, we can multiply by a matrix, right? That makes sense, right? Now, we have what are called these phase retarders. So in this case, we want to talk about half wave plates. We have a phase retarder, which basically just delays one of these, the electric field from one of these components. So let's say the Y component is phase delayed. Now, we want to know what happens if we take this retarder, okay? Here's an example of a quarter wave plate. These are glasses from Real D. These are 3D glasses. These actually have a half wave plate. Actually have a quarter wave plate in. No, not quite the same thing. But if you take your half wave plate and you rotate it, okay, you can represent that by this rotation operation. Okay, so the rotation matrix. Okay, and if you just work through the math, you just solve for this here. What you find is that if you put in right circular polarized light for a half wave plate where this phase is given by pi, okay, then what comes out is left circular polarized light. But what is more, introduces phase. This phase is twice the angle of the rotation. Okay, this rotation angle is just theta. The phase changes by twice that amount. Okay? So what it means is that I can take a bunch of little half wave plates, each one of them at a slightly different rotation angle. I can make any optical element you want. You want a lens, I'll give you a lens. You want a prism, I'll give you a prism. You want a gradient, I'll give you a gradient. You want something exotic, a vortex, I can give you a vortex. Okay, so this is what the Beamco company is doing, is they're making these devices using liquid crystals to achieve this. Now, I'm not going to talk about, I don't have time to talk about gratings. about our advanced gratings that Ryan's working on. He's basically trying to make these hybrid gradients where some of the light is reflected, some of the light is transmitted. We're trying to optimize the radiation pressure on these structures here. The main idea is that when you have diffraction, light comes in of different colors, let's say sunlight comes in, and it scatters off depending on the wavelength. And so we need to try to optimize the kind of the average scattering distance, the scattering angle for this system to get the most force. And that's what we're working on here. Okay, and you can do Fourier optics. You know, anybody recognize this? This is basically the Fourier series representation of a gradient. Basically, it says whatever your electric field is, you multiply this by this Fourier kernel, if you like. Okay, where capital K represents the period, basically 2 pi over the period of the gradient. And you can basically just do this integral to find out how much light is diffracted into these different orders. Okay, M is the diffraction order here. So it's a very beautiful, very complete theory. And you can basically work through and find out what the radiation pressure is for sunlight. And you get kind of a funny looking spectral distribution of the force or the efficiency on the sail. The main thing is we found is that for this gray curve here, this little gray oscillating curve, for a long period gradient, 10 microns, for a short period gradient, it oscillates a lot more. So it basically tells us we really kind of want a long period gradient. Probably the long period gradient's probably going to be heavy. So there's trade-offs to be had here. So we're looking at various different, like I said, the metamaterials, we're looking at the polarization gradients, and we're looking at conventional gradients to solve this. Just real quick, this is what our system looks like. This is what NASA came up with. We have basically our platform for waste in the solar cells can be stored in here inside of this fairing. And it basically has a whole bunch of kind of standard components associated with it. They want to first spiral inward and then spiral upward. The idea is that it takes about three years to spiral inward to 0.48 AU, and then about 10 years to crank this thing up over the poles of the sun. And so it's going to be a 16-year mission. 3 years of that will be direct observing at 0.48 U, but as it spirals in, you're going to also be able to take science data along the way. Okay, this shows basically the sail, though. The science payload is going to be basically in the center region here. There's a little cutout pattern here. And it's going to have solar rays for producing electricity. So you can take pictures and beam them back to the Earth. It's going to have these heat radiators on it. It's going to have a boom for detecting the magnetic fields and the particle fluxes. So it's going to have a number of instruments on it. And so all in all, this project pulls together a whole lot of necessary parts that involves the theory of modeling, experiments, fabrication. And as I suggested earlier, we really want to pull in even a wider community in imaging science to help us with the remote sensing of the sun for this, and to develop kind of a new thrust in the center if folks are interested. Okay, so I'm looking forward to your feedback, see what you think about the possibility of driving this thing forward. So thank you for coming. I'll take any questions now. Appreciate it. Yes. Go ahead. Who's got a question? I'm just gonna point to anybody. Yes.
Can you explain how the stereo pair works?
Yeah, so you're gonna have two basically orbiting around the sun, right? So yeah, they're gonna be going in tandem. Maybe it's 36 degrees apart. It's not clear what angular distance you're gonna need at this point to actually get the most opportunity to assess what the volume of this plasma stuff is. And it may be even variable because we have some control over that distance.
Okay,
But that's
just curious how far apart.
yeah.
I guess it doesn't really relate to astrophysics, but there's another Carl-Sagan photo, like, talked about in the 90s in the future, technology would be in the hands of few individuals, critical thinking would be fun.
Let's hope not.
But already happening.
John?
Very impressive. So what's the next step? You've got this proposal, it's gonna cost $144 million. What are the chances that
Yeah, so Amber's working with APL to try to get some internal money right now. We have folks at NOAA who are interested in seeing this thing fly, so we might be able to try to get some money from them. Money's always tight, right? So it's it's best to ask for money after the disaster happened, and then people can say, oh, why didn't we do it earlier, right? So we're trying to get ahead of that ball, but I mean, during the solar maximum seems to be an ideal time to start getting people to think about, yeah, how much is at stake. Yeah, try to get a mission. Our mission right now is to basically get like a CubeSat type or a small satellite up above the Earth and demonstrate diffractive solar sailing. So we can basically show how these diffractive things work. Besides just sailing, they can be used for like momentum management. So one of the biggest problems with satellites is that they tend to spin and you need to kind of despin them, and there's always perturbations. And so they use gyros for doing that, and as gyros get saturated, you can't basically get any more extract any more momentum control out of that. So you need to basically desaturate the wheels. And so you can use radiation pressure, for example, to help to desaturate your momentum wheels. So there's a lot of things that besides the solar cells, that this stuff could be important for not, big sail projects, but even for smaller satellites. Thanks. Yes.
What are some of the technical challenges you face while pursuing this apart from the funding and complex math? I'm just curious of how you go on about it.
Yeah, so far we haven't beaten reflective cells. So the reflective cells are really nice because they're simple, and they basically, even though you have this projection angle problem, they are pretty good. And so try to find alternative approaches to that is what, basically looking at the theory and fabrication issues. Diffraction gratings on paper are really nice, but there's like every system, there's the stuff that basically you've shoved under the rug, and that can come back and kind of be a problem. So we're looking at trying to look at alternatives for that. So the physics is a challenge, and it's kind of fun, and we're doing a lot of stuff to explore that.
How do you protect the optics? I'm also curious about that.
How do we what?
The optical instruments, like whatever.
Or how do you protect them?
Yeah.
Yeah. So they're basically we're not that close to the sun. We have to worry about heat. Okay, so the heat is not a big issue, and so yeah, they're basically just standard kind of shielding. We can put Mylar around them, put metal boxes around them to try to keep them from charging and things like that, and keep them closed until they need to be open. Yeah, the cameras and stuff like that are not a big issue in terms of the orbit that we're at is pretty conventional imaging stuff.
And how far from the magnetic solar flares, right?
Right.
For them to not like get attacked by the solar flare itself.
Right. I mean, the space is very harsh. So UV is a killer. Okay, and the particles, charged particles, from basically an alpha, beta, gamma particles can come in, and they can basically damage your electronic components. Okay, so making them radiation hardened, as they call it, is a big challenge. And so that's why these missions don't last forever. Okay, 3 years, and it might be okay. We know it's going to die. Okay. Back there, anybody? My former students? No.
So this question might be funny, but I'm not that familiar with how laser works, but could you put the laser on the instrument and let it shoot the sail and push itself forward?
No. So basically, that kind of violates some laws of basically momentum would be conserved there, and so you wouldn't be able to put it on and do it that way, because there's going to be basically equal and opposite forces that wouldn't work. So you need to have if you want to have a laser, it could be on a separate platform and do it that way, but it couldn't be on the same platform. You could just shine it away. I guess you could think of maybe trying to shine something away. But then the mass of that system is going to be so huge that it's still not going to end up benefiting you. Yeah.
Has this solar sailing technology been applied in a smaller scale, or where?
So with the Planetary Society, well, it was a demonstration mission. The Japanese did a small demonstration mission called Icaros. And NASA launched what they call Nanoscale D. They also did a demonstration mission. So there's been three. I think there's actually fourth one about ready to go up that Langley is going to put up. So yeah, they're coming out, step by step. The Germans are very active in developing solar cell technology. Chinese, Japanese, Canadians. Yeah, so it's a worldwide interest in doing this because you can do missions you couldn't do otherwise. So it really is enabling. Okay, thanks for your attention. Thanks for your questions.